Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Hello everybody and welcome to this presentation. In the previous section, you learned how to design a membrane in 4 lectures. Concepts before the design, reverse osmosis design in 10 steps, evaluation of membrane system performance, energy and sustainability considerations. Now, as a membrane designer, you have to be able to analyze the membrane cost and capacity. This lecture presents an overview of the cost of desalination and the main components of associated capital cost and operation and maintenance cost. Examples of desalination facility costs have been presented to illustrate the range of costs that can be expected and to aid in conceptual planning and development of desalination projects. For this reason, we go on the course with this lecture, water desalination using reverse osmosis and nanofiltration membrane, cost and capacity. As always, let's look at the content. In this lecture, at first you will get some information about desalination market capacity, then major impacts on desalination cost, capital and operation and maintenance cost, reverse osmosis plant unit production cost versus project capacity, typical life cycle cost comparison of MSF, MED, and SWRO, comparative cost of the major desalination technologies, and at the end we have a case example. Desalination market share and trends. The most prevalent forms of desalination can be divided into 2 technology types. First, thermal desalination, using heat energy to separate distillate from high salinity water, represented primarily by multiple effect desalination or MED and multi-stage flash desalination or MSF. Mechanical vapor compression or MVC is primarily used to desalinate high TDS bigger than 45,000 mg per liter and or industrial wastewater for the purpose of reuse and not necessarily potable uses. The second technology is reverse osmosis membrane separation, which uses a membrane barrier and pumping energy to separate cells from high salinity water, typically less than 45,000 mg per liter. Desalination technologies are capable of treating water from a wide variety of sources, including but not limited to brackish groundwater, surface water, seawater, and domestic and industrial wastewater. As desalination technologies have developed and improved, the cost to build desalination plants has declined. This decrease in cost has been one of the primary factors for the acceptance, growth, and success of desalination. This figure shows how capacity has grown rapidly in the 21st century. Total desalination capacity exceeded 64 million cubic meter per day in 2010, and was close to 98 million cubic meter per day in 2015. Growth and installed capacity by region. In this figure, desalination capacity by country has presented. The largest production capacity by location is in the Middle East due to their lack of freshwater sources and abundant energy resources as can be observed in these figures. The largest desalination user by capacity is in Saudi Arabia, followed by the United States, UAE, Australia, China, Kuwait, and Israel. The top 15 desalination markets for a 9-year period from 2007 to 2016 is shown in this figure. The United States has shown the largest increase in installed capacity since 2012. This figure shows installed capacity versus technology. The predominant type of desalination technology used today is reverse osmosis. The use of reverse osmosis has been a trade-off between low operation and maintenance costs versus high capital costs. Over the years, membrane prices have reduced dramatically and membrane life has increased due to better feedwater pretreatment and a better understanding of how to operate reverse osmosis systems. This figure illustrates desalination market share by the end user application. Municipal use for desalination comprises the largest portion of the total installed capacity, followed by industrial, power, irrigation, and tourism uses. The factors such as capacity, location, type, and application have a significant impact on cost. There are other important site-specific factors that directly impact desalination costs, which are discussed in the following slides. Major impacts on desalination costs. Factors that have a direct and major impact on desalination costs include, but are not limited to, desalination technology, the location of the plant or project, raw and product water quality, type of intake and outfall, pretreatment, the type of energy recovery used, the price of electricity, post-treatment needs, storage, distribution, local infrastructure costs, and environmental regulations that I'm going to discuss each of which. Desalination technology. Almost 95% of the installed desalination capacity today is either thermal, around 35%, or membrane-based technology, around 60%. Each type of system varies considerably in footprint, materials of construction, equipment, pretreatment requirements, power and steam requirements, amongst other differences. The technology selection will also determine the type of chemicals that will be used for pretreatment and post-treatment, which impact operational cost. Location. The site where a desalination facility is constructed can have a major impact on the overall cost of the project. For example, for a seawater reverse osmosis desalination plant, the plant should be located as close as possible to the seawater intake source to avoid higher costs for intake pipelines and complex intake structures. Optimal project siting will also reduce the concentrated brine discharge line back to the sea. From a construction point of view, careful considerations are recommended for items such as local soil conditions, and close proximity to a reliable power source to reduce the power transmission cost. Raw water quality. As we have already discussed, in addition to considering raw water quality as the first step in the membrane design, the site-specific raw water quality can have a major impact on the number and type of pretreatment steps required ahead of the desalination step itself and the overall sizing of the desalination plant. The total dissolved solids level of the source water directly impacts the operational cost as higher operating pressure and temperature must typically increase as raw water salinity increases. Higher raw water salinity may also reduce the feasible product water recovery of raw water for both reverse osmosis and thermal systems. Intake and outfall. The type of intake and outfall selected for a desalination plant is one of the most important technical considerations for a plant's cost-efficient design and optimum operation. Important factors need to be evaluated such as the most suitable intake type, the distance of the intake relative to the plant, the type of intake screens, the type of intake structure, the type of intake pipeline, and environmental considerations with regards to marine life. Each of these items has a significant cost impact. Pretreatment. Pretreatment costs are impacted by the type and complexity of the pretreatment system. The type of pretreatment required depends on the raw water quality at the project site. Some raw seawater or brackish surface water sources have a high level of organics and biological activity and require more robust pretreatment technologies such as dissolved air flotation and ultrafiltration. Other raw water sources that use submerged intakes or well-based intakes may require less pretreatment, such as a single-step media filtration or microfiltration. Pretreatment costs are typically greater if the water source is wastewater. This may be due to many factors such as the necessity to remove high calcium and magnesium levels, the addition of chlorination and dechlorination steps to destroy microbes, or the necessity of using ultrafiltration to remove high molecular weight organic compounds. Energy recovery. Reverse osmosis systems use high pressure pumps to overcome the osmotic pressure of the raw feed water. For example, some seawater reverse osmosis plants can require up to 70 bar feed pressures. The reverse osmosis concentrate brine stream from this process contains pressure energy that can be recovered in order to reduce the overall reverse osmosis system energy requirements. Energy recovery technologies reduce the overall energy input, thereby reducing operating expenditures. Electric power. Local energy prices, transmission distance, connection fees, and possibly tariffs at proposed location of the desalination facility play an important role in determining the supply price for connected power. Post-treatment. Final product water quality will determine the specific type of post-treatment that is required. Post-treatment steps add additional cost. Post-treatment costs are typically greater if the water source is wastewater. This may be due to many factors such as post-treatment oxidation to inactivate viruses and higher costs for waste brine or solids disposal. Local infrastructure costs. Infrastructure costs include items such as earthworks, concrete, steel, structures, drainage, and building materials. Depending on the location of the plant, the cost for each of these items can vary significantly. Environmental regulations. Each geographic region will have its own set of environmental rules and regulations, and this can also vary from state to state within a single country. Cost components: capital cost, operation and maintenance cost. Membrane costs include investment cost and operating or ongoing cost. Investment costs such as construction material, operating conditions, and production capacity. Operating or ongoing cost is subdivided into the two major categories: fixed operation cost and variable operation cost. The major components of fixed operation costs such as depreciation, maintenance and repair, insurance, membrane replacement, personnel cost, and analytics. Chemical and acid substances, energy, waste, and bypass disposal can be included as variable operation costs. In this slide, typical seawater reverse osmosis desalination plant capital and operating costs have presented. The typical capital cost and components for most desalination plants can be further divided into 9 parts as follows: intake and raw water conveyance, pre-treatment, desal treatment, post-treatment, product water pumping and storage, electrical and instrumentation system, plant buildings, site and civil works and balance of plant, brine discharge and solids handling, and miscellaneous engineering and development costs. Other costs such as financing fees and other commercial related fees also have to be considered. Capital cost to a significant extent depends on a scale, with larger desalination plant costing less per $1 million of installed capacity. Based on this figure, a medium-sized $10 million per day seawater reverse osmosis plant would cost about $80 million to build. The typical operating costs and components for most desalination plants can be further subdivided into 9 parts, comprising the following: power consumption, consumables, solid waste, chemicals, labor, maintenance, equipment warranty, balance of plant and utilities, and other fixed costs as shown in this figure. Reverse osmosis plant unit production cost versus project capacity. This figure shows that annualized costs for various types of completed reverse osmosis projects have varied widely. The average cost, represented by the best fit line in the data shown, are about $0.70 per cubic meter. For very large plants, around 325,000 cubic meter per day, and rise to $1.25 per cubic meter for small plants, 10,000 cubic meter per day. The cost to desalinate industrial wastewater for reuse can be much greater than this. This figure also shows a typical life cycle cost comparison of multi-stage flash desalination, or MSF, multiple effect desalination, MED, and seawater reverse osmosis to produce 1 cubic meter of water per day. As shown, MSF and MED, which are thermal desalination technologies, require steam or thermal energy in addition to electrical energy, which is the main reason why they have higher total water life cycle cost compared to seawater reverse osmosis. Comparative cost of the major desalination technologies as a function of salt concentration. This cost should be taken as a guide only. Site-specific factors can affect cost significantly. The relative cost of reverse osmosis compared with other desalting technologies such as ion exchange, electrodialysis, and multi-effect evaporation is shown in this figure. The operating cost of the electrodialysis and ion exchange scale almost linearly in proportion to the salt concentration in the feed. Therefore, these technologies are best suited to low salt concentration feed streams. On the other hand, the cost of multi-effect evaporation is relatively independent of the salt concentration and is mainly proportional to the mass of water to be evaporated. Thus, desalination by evaporation is best performed with concentrate salt solution feeds. Reverse osmosis costs increase significantly with salt concentration, but at a lower rate than electrodialysis does. The result is that reverse osmosis is the lowest cost process for a stream containing between 3,000 and 10,000 ppm salt. However, site-specific factors or plant size often make the technology the best approach for more dilute feedwater or for streams as concentrated as seawater through 5,000 ppm salt. Examples of desalination facility costs. As noted in this lecture, the cost of developing, constructing, and operating a desalination facility depends on the location of the plant, the raw water type and quality, type of intake and outfall, the desalination technology and energy recovery stream used, the cost of electrical power, and required post-treatment and storage, distribution costs, and environmental regulations. These differences can make a large plant built in one region of the world more expensive than a smaller plant built in another region of the world and result in significant differences in operation and maintenance costs. This is illustrated by the projects shown in this table. As you can see, there are three projects in different locations in the world that compared. Projects in the USA, Persian Gulf, and Australia. The parameters that compared for this project that affect the cost such as plant location, plant capacity, plant recovery, raw water salinity, product water quality, intake type, pretreatment type, desalination technology, energy recovery type, post-treatment, storage and distribution, brine discharge, environmental regulations, and specific energy. As you can see, the plant capacity for the USA is larger than the others. The plant recovery is almost the same. Raw water salinity for the Persian Gulf is higher than the others. Product water quality for the Persian Gulf is also high. Intake type for all three is open intake. Pretreatment type for the USA and Australia is the same, but for Persian Gulf is this of gas flotation followed by filtration. Desalination technology for all three are the same with two-pass seawater reverse osmosis. In post-treatment, carbon dioxide and lime addition and chlorination applied for all three. Storage and distribution for these projects is different, but for Persian Gulf is not available. The brine discharge for the USA and Persian Gulf direct to sea, but there is 300 meters distance for Australia. There are differences in environmental regulations for these projects. In the USA is very stringent, for the Persian Gulf is moderate, and Australia stringent. The projected lifetime for these projects 20 years considered. The capital cost for the USA and Persian Gulf not available. You can also compare the operation and maintenance costs for these projects. The unit production cost for the USA is $1.86 per cubic meter per day. For the Persian Gulf is less than $0.60 per cubic meter per day, and for Australia is $1.63 per cubic meter per day. Now this lecture finished. In the next section, we have a case study and we will discuss more about the membrane design and cost and capacity. Thank you for your attention.